Yes, class. Is it audible now? Sufyan Taha. Now, see, we have started with magnetics chapter, and I have told you that we are currently doing magnetics, and you will be doing it with the second batch. All right. So, one thing, we left the second chapter in between, right? As to complete the portions. Now, in the extra class, you will be completing the magnetics. So, we have two chapters which we have to discuss meanwhile you are studying magnetics, right? One is this potential one, which we have started, and another one is current electricity. So the circuits portion, these are interlinked, but we have to study, right? Both the chapters, we cannot leave them. So pay a little attention while you're studying, because now you have to get the extra classes done. See, the reason is that you joined the batch late. This batch was formed a little late. That's why we are having this issue. Otherwise, we wouldn't have got this issue. Now I'll start with equipotential surface. So whatever we have discussed in potential, I'm just revising it quickly. So basically potential is the work done, which is required to move a charge from a point, from infinity to a point, right? That is what is meant by the potential. It's the work done, right? So formula also we write, work done is potential by charge. Like this we write. Potential is work done by charge, right? This is the formula which we write. Then potential due to a point charge is kq by r. These are the two things which we had studied. Now, what are equipotential surfaces? This is a very easy topic and we'll cover it very quickly because it's very easy, it's theoretical. And from the term equipotential, what do you understand? Equi means equal, potential is voltage, potential which we have studied. So equipotential means a surface at which all the points are giving you the same potential. Surface at which every point has the same potential, right? So if this is, look at this example, this is a circle with 2 volt at A point, 2 volt at B point, 2 volt at C point. So if I'm choosing any point, I am getting 2 volts, right? So it means VA is equal to VB. This is equal to VC. So all the values, these are giving me just 2 volt, right? So in these cases where I'm getting 2 volt as my answer, now this surface, this becomes an equipotential surface. Equipotential surface. Like, look at this example. These are three surfaces. So it's not necessary that it has to be a perfect circle or a symmetrical figure has to be present in order to make the surface equipotential. No, if this is a random surface and still we are getting VA is equal to VB is equal to VC, we'll get the same potential. All right. Now, what are the properties of these equipotential surfaces? First property is in the definition only. That potential at every point on the equipotential surface is same, right? So potential same hoga, that is the first point. So VA is equal to VB is equal to VC. Then the surface is called equipotential. All right, then we say the surface is equipotential. Now, secondly, we have this second definition is class one thing. If the potential is not changed, fine. If at VA is let's say 2 volts, VB is also 2 volts, VC is also 2 volts. So if we are getting these values, now class change in potential will be what? Can anyone tell me what will be the delta V's value? Yes, class, if potential is same at every point, then what will be the change? Can anyone answer?
0.
0. It will be 0. Because same values you are subtracting, you will get 0 only, right? You will straight away get 0. So work done in such case, this is 0. So for equipotential surface, remember this. Work done, this is always 0. All right. Then one more property. Electric field is perpendicular to the equipotential surface. If you see a surface, you see that it's equipotential, straight away draw electric field lines perpendicular to it. All right, electric field lines are drawn perpendicular to the equipotential surface. Now class, Next point says that if all the equipotential surfaces are drawn very closer to each other, like this, and then there is a gap. So basically it shows that wherever electric field is strong, equipotential surfaces are placed closer like this. If there's a gapping, it means equipotential surfaces are far away from each other comparatively. Comparatively, I've mentioned on the screen too. Comparatively means it's not very far as in we take in the dipole, but a significant distance is present. So these are the properties. What are the properties? Firstly, potential is same at every point. Second, work done will be zero because the potential is same at every point. Third, electric field is drawn perpendicular to equipotential surface. And fourth, that strong equipotential surfaces represent closer equipotential surfaces represent a stronger electric field, and far away equipotential surfaces or distant equipotential surfaces represent weaker electric fields. Write it, then we'll see how to draw the equipotential surfaces. Continue it from wherever you've left writing. You can manage this in your registers now, because now 2 classes will be going. Write down this. Okay, now the next is how to draw an equipotential surfaces. So you will get certain quantities, like you can get a positive charge, you can get a negative charge, you can get combinations of these charges, like positive, positive, negative, negative, positive, negative, like this. So if we have isolated point charge, then suppose plus Q is present and around that we have charges which are present. All right, so isolated point charge and then around the charge these equipotential surfaces are present. Then if you have two positive charges, what would be the difference? See, around the individual charge, these concentric circles will be present. But the difference is that if you have positive charges, since they repel, so that's why these lines which are far away from the charge on the opposite edges appear to look closer, and these which are in vicinity appear to be a little distance or thick. Okay, and same with the negative charges, minus q minus q. The peripheral ones become negative and the central one become thicker. All right. So like this you have to draw. But if we have the opposite case, means one positive, one negative, that is known as a dipole, right? So here the opposite occurs, means in the central portion will be thinner and the outermost portion will be thicker. This is the difference that will come. Now, when we are talking about the electric field placed in uniform, means basically dipole equipotential surface placed in electric field, which is uniform. This is what is written. Our equipotential surfaces are placed in a uniform electric field. So what will happen? The distances between the potential equipotential surfaces would be the same. If this is D, this would be D. But if it is a non-uniform electric field, then see, this is D1, this is D2, and you can clearly see D1 is greater than D2. So this is how you have to draw, and these come in the exam. Okay, equipotential surfaces, very easy questions are asked. No difficult question is asked from this topic. But yeah, the direct questions are also asked, so you have to practice, right? Write it down. This completes with equipotential surfaces. We'll then start with potential of a dipole. Dipole is left in potential, right? Write it down. C class, now we have to discuss the potential of a dipole, but first understand this diagram. So these are two charges which are present, plus Q and minus Q. They are separated by this distance, which is 2a, right? This is what we did. So from this point, P point, plus Q is separated by R1, and from this minus Q it is separated from R2. And from the center of the dipole to the point of calculation, we always take R, right? Now two perpendiculars we have dropped, this one on this and BD here, right? Now this is theta, here also we have theta. Okay, so this is the figure. I've just zoomed it so that just in case if in smaller view, if you've not understood it, you can relate. Now see, let us see the derivation. Firstly, before any derivation or anything, you know what's the potential. Potential of the plus Q charge is KQ by R1. Potential of negative charge is minus KQ by R2. Right, that's what is the potential. So potential can be written as KQ can be taken common. 1 by R1 by 1 by R2 can be taken aside, right? Now, see, in this figure, we have dropped the perpendiculars. Why? What was there in, what was the need to do this? Reason is that to make them almost similar, equal in length. These weren't equal, right? This can be equal. So see, PA is almost equal to PC. And how can I write PC? PC can be written as PO then plus OC, right? PO plus OC. PO plus OC, right? Now, what is PC? PC is this entire, right, which we have replaced. Now, what can we write PC equal to? We can replace it with PA. That's what we have written. PA and PC, they are similar. So, PA is also equal to PO plus OC. Reason? They are exactly equal. What is PA? PA is this R1. What is PO? PO is this R. What is OC? OC is this, right? Now, in triangle AOC, if I write what is cos theta? So in this, if I have this is my angle, cos theta will, or if this is the angle, cos theta will simply be OC by AO, right? This will be OC by AO. OC by AO. So AO is small a, right? Half of the distance. So OC is equal to A cos theta. Now can I replace all the terms here? Look here, what can I replace? I can write PA as R1. I can write PO as small r. I can write OC as A cos theta. One equation which we have received. Similarly, look at the second triangle. Now here in this second triangle, actually this smaller ones are now equal, right? If you look in this figure, PO and PBs, they are now equal, right? So if such are equal, right? What we have to do? Here you have PO. It means we can replace PO with PB anytime. Correct. So what do we have to write? Firstly, PO is equal to PD, right? PD plus this DO. This entire PO is made up of PD till here, then from here DO. So what can I write? PO is equal to PD plus OD. And PO, I can replace PD with PB, right? So PO is PB plus OD. So let's bring PB here. PB is equal to PO minus OD. What is PB? PB is R2. What is PO? PO is R. Now again OD. So if you write cos theta in the smaller triangle now see what all things are present if you write the smaller triangle. This is the theta. So you have OD by OB. OD by OB, right? OD by OB. So this is OD by OB. So what is our OD equal to? OB is A. So that becomes A cos theta. Right? This is OD by OB. So OD is equal to OB into cos theta. OB is A. So OD is A cos theta. So if we replace this as A cos theta, this becomes minus A cos theta. This is the second equation which we have received. Now we have R1 value, we have R2 value. R1's value can be put here. R2's value can be put in this main equation. This is our main equation. So how would it look like? This will be 1 by R1 is this now, minus 1 by R2. So this is KQ, 1 by R plus A cos theta minus 1 by R minus A cos theta. Now, till here was your physics which you had to apply. Now, all you are left with is just simple mathematics which you've already studied in your class 10th, right? So what is this? You have to take the LCM first. Yes, class. So R minus A cos theta and one is R plus A cos theta. When you multiply them, so R minus A cos theta minus R plus A cos theta divided by R plus A cos theta into R minus A cos theta. Let us open up the brackets. If we open the bracket, this will be KQ is already here. This will be R minus A cos theta. This is minus R. This is minus A cos theta. And this is R square minus A square cos square theta. So this is R minus R. So this will be, see, this is K minus, actually minus KQ. And this is minus A cos theta minus A cos theta, which is minus 2A cos theta. So minus I have already written. So 2A cos theta divided by R square minus A square cos theta. Right? Now class, have a look here. Q into 2A. Q into 2A, this is equal to the dipole moment P. So V is equal to Kp cos theta by R square minus A square cos square theta. This is the formula for the dipole at any angle. Now you can take any angle because this is a generalized formula. We have not written any specification about this. This is the complete generalized formula which we are writing. Right? Now, if we are talking about axial and equatorial line, one thing if you approximate it where R is very much greater than A, then this entire term in the denominator can be replaced by R square. So this is the formula which we use, Kp cos theta by R square. Now, if you have axial and equatorial, one thing is very simple and clear cut over here, that theta will be 0 degree. So V is equal to Kp cos 0 degree by R square. It is equal to, this is equal to, V is equal to Kp by R square. This is the formula for axial. But here theta is equal to 90 degree. Why? Because here, see, it was on the axis. Now this is perpendicular. So this is making 90 degree. So V is equal to Kp cos 90 degree by R square. So simply potential is 0 at the equatorial line. This is important. This is asked in the objective questions also. Tell me, Taha, Sufyan, both of you, is this entire topic clear to you? It's very important.
Yes.
Yes, sir.
Okay, good then. Write it. Any queries in between, please let me know. Start writing this derivation. This derivation is important. So mark somewhere that this derivation can come as it is to write in the exam, because questions are based on this, and derivations have come on this because it includes both general, axial, equatorial. Right. Yes, class. Now, I hope you've practiced this question once. Two charges are there. They are placed at separation minus A plus A, means the separation one is at A from the center, other is at A from the center again. So total distance that we have here is 2A, right? First point, potential at point A, 0, comma 0. A is the 0, comma 0, comma Z. So V is equal to C. This point A is lying on the axis of the dipole. So it will be KQ minus KQ by C. Not KQ, it will be KP. KP by, instead of R square, we'll have Z square. But what's the entire formula? Let's not take the shorter one. R square minus this entire thing. So this is A square. R square means from the center the separation. So it's better if we straight away use Z square, right? This is the first part. Second part says same thing for B point and C point. See, when you are calculating it for B point, B is situated at x comma y, right? This is the distance. So it is exactly perpendicular to this axis. So B will be 0. Why? Because it is making 90° with the axis, right? Plane is making 90° with this axis. Similarly, C point is also perpendicular to Z axis. So C point will also be 0 because both of these are 90°. 90° means equatorial. Third point, work done in carrying proton from B to C. So B to C work done. See, third part, if change in potential is 0, because VB is equal to VC, which is 0, so work done will straight away be 0. Last part, does work done depend upon potential between B and C? See, work done, this is all these are conservative forces. Work done is conservative in nature. Now, what is meant by conservative? Suppose you have A point and here you have B point. This is the initial point A. This is the final point B. So from A to B, you go like this. From A to B, you go like this. Or from A to B, you go like this. Work done 1 is equal to work done 2 is equal to work done 3 in case of conservative forces. This is what is meant by a conservative force. So yes, it is conservative. Potential is conservative in nature. So our answer is yes. Write down the solution. Okay, class, now we have one last topic for today. So basically, relationship between electric field and potential we see. Electric field we have studied in the first chapter. Potential we have studied in the second chapter. Now there's a connection between electric field and the potential. So what is this connection that we are going to see? There's a little small derivation which usually comes for 2 marks, or maximum it can come for 3 marks. That will be asked. I think you have your test today, or you had it. Magnetism. All the topics which we have done in the class from Biot-Savart's law are only going to come. So yes, work done in carrying a charge from A point to B point. Now we've already studied in the first chapter that force is equal to QE, and here the distance that we have taken is dr. Now from your work, energy and power, which you've studied in your class 11, you know work done is equal to force, that is QE, into displacement, dr, right? This is one equation which we have. Second equation is from this chapter only, that Q into dV. So let's equate these two. This is our first equation. This is our second equation. Both are giving us the work done only. So we can equate both of these equations, right? Since they are leading to one physical quantity, we can equate it. So Q into dV is equal to Q into E into dr. Charge get cancelled from both the sides. So you have electric field which is equal to dV over dr. Now, how do we write this formula completely? We write it with a negative sign. Now, there are two things, class. If something is changing with respect to time, we use the word rate for time, something which is changing over a period of time. Now, if something is changing with respect to position, like here the potential is changing with respect to position, we use the term gradient for this. So basically this formula is leading us towards the relationship between electric field and potential, and concluding that electric field is a gradient of potential, right? Electric field is directly proportional to the potential gradient. This is our derivation. Very small derivation, usually it comes for 2 to 3 marks, but this formula has a lot of significance. This is very important. This we'll be dealing in detail because this is important and it comes in the exam too. This portion I'll tell later. First, write down this.